In the last lecture, we calculated the force experienced by a charged sphere due to another using Coulomb's law. We modelled charged spheres as point charges, which is a good approximation when the distance between them is much bigger than their size. But what if the system doesn't resemble point charges? What if we had, say, two charged wires next to each other, or two charged spheres with radii roughly equal to the distance between them? How would they interact with each other? To tackle these problems, we seek a more general way to think about the interaction between charges. This brings us to the concept of the electric field, a powerful mathematical framework for understanding how charges influence the space around them. Let's start with a positive point charge, Q1. If we place a small positive test charge, Q2, at a point P2, we can find the force on it using Coulomb's law. The electric field is defined as the force per unit charge that a small positive test charge experiences at that point. In other words, in this example, the electric field due to Q1 is the force that Q2 experiences divided by Q2. As the force is in newtons and the charge in coulombs, the electric field has units newtons per coulomb. As the force is a vector and the charge is a scalar quantity, the electric field is also a vector. In our example, where we can find the expression for the force from Coulomb's law, the electric field E is Q1 divided by 4 times pi times epsilon naught r squared, all times r hat. The electric field of a charged object tells us how the charged object influences the space around it. Using our expression, we can calculate the electric field due to Q1 at any point in space. If we calculate this at a few points in space, we get a neat vector field. We've calculated each of these arrows using our formula for the electric field, while varying r and r hat. As stated in the previous lecture, the magnitude of the vector is contained in this part of the expression, while the direction is given by r hat. If you are not fluent with how to calculate these, here is an example for a point in our system. It can be quite fun to see how the electric field due to Q1 varies, as we vary the value of Q1. As you would expect, if we change Q1 from positive to negative, the field changes direction. Now there's one key thing we need to stress here. The electric field is the direction of the force that a positive test charge will feel. This is the agreed convention, and is because of our definition for the electric field. As we'll see for more complex systems, we usually derive the force from the electric field, rather than the other way around, as we did here. Rearranging our expression, the force a test charge Q2 experiences is just Q2 times the field. So if Q2 is positive, the force will be in the direction of the field, while if Q2 is negative, the force will point in the opposite direction of the field. This is important, as in later lectures, we'll often consider the movement of electrons, i.e. negative charges, which will move in the opposite direction to the electric field. We can also calculate the electric field for a system of point charges. As with the forces in the previous lecture, the electric field at each point is now just the sum of the electric field contributions due to each charge. These are summed with vector addition. It can be quite fun to experiment with the pattern by varying the values of the charges. As with before, if we put a positive test charge somewhere in this field, it will experience a force in the direction of the field, while if the test charge is negative, the force will be in the opposite direction to the field. We can also visualize the electric field using field lines. Field lines are simply paths that follow the electric field vector at each point in space. In other words, if a test charge was let go and allowed to start moving, it would move in the direction of the field lines. The great thing about field lines is that you can make a good guess of how they should look, without having to really calculate anything. The key rule to remember is that the electric field always points away from positive charges and towards negative charges. This system of point charges is actually a relatively complex example, but for many systems we'll encounter, the direction of the field is usually very obvious. Here's a neat plot for a positive and a negative point charge. If you were wondering, you can actually calculate the exact paths of the field lines too, which is what I did to make these plots. As this requires a fair bit of calculus, and is beyond even most university courses, I won't go into it here, but if you are curious, you can look further into the work of Michael Faraday, who came up with the idea of the electric field in the first place. We should also note one more key point about electric field lines. The higher the density of field lines in a region of space, the stronger the field is there. In our example, I have drawn 16 field lines per point charge. As you can see, there is a higher density of lines near the charges, and a lower density away from them. You can draw as many field lines as you like, and you'll always see that this is the case, as long as the lines are evenly spaced and drawn properly. This, of course, matches our calculations, where Coulomb's law states that the strength decreases as we move away from each point charge. So far, we have calculated the electric field for a system of point charges. This is all well and good, but it hasn't really added much to what we already knew from Coulomb's law in the last lecture. It turns out, however, that we can use this idea of the electric field to figure out how charges behave around more complex charged objects, rather than just point charges. Systems of point charges are also known as discrete charge distributions, as they consist of discrete points where charge is located. However, in most real systems, like wires, charge spreads out over a region in space. We call systems like this continuous charge distributions. So how do we find the electric field for systems like this? Well, before jumping into the maths, let's see if we can guess what the field might look like purely from our intuition. I will note again that for the sake of visualizing this, I did calculate the field lines precisely, but you could easily sketch these patterns with a pen and paper without any of that knowledge. Let's do this for a simple positively charged wire. Hopefully, you could have sketched something like this yourself. Just remember, the field lines point away from positively charged objects and toward negatively charged objects. A really neat charged system that is often taught in schools is that of two charged plates, one of which is positively charged and the other equally negatively charged. In our diagram, we are viewing the plates side on. This system is known as a parallel plate capacitor and is used in pretty much any electrical device you've ever used. We will discuss capacitors in more detail later in the course. As we know the electric field points away from positive charges and towards negative charges, we can once again sketch the electric field intuitively. There are a few interesting features of this. Near the center of the plates, you can see that the field lines are almost completely straight, and that the density of field lines is virtually constant. It is only near the edges of the plates that the field starts to vary significantly. Let's now pretend that our parallel plate capacitor is infinitely large. When we do this, we find that the electric field becomes fixed everywhere within the plates. We find that the direction is fixed, directly pointing from the positive to the negative plate, and that the density of the field lines is constant. So, the strength and direction of the field is fixed everywhere. This is also known as a uniform electric field. The infinitely large parallel plate capacitor is often used to teach electric fields in school because it is one of the only systems where the electric field is uniform like this. There is one small nuance we should mention here, in that we are also assuming that the charge within each plate is uniform, meaning that it is evenly spread out within them. If there was more charge at one point within the plates than others, the field would vary. Now, I really want to show you why the field is uniform between these plates, but to derive the expression for the field requires far more advanced mathematics than we have dealt with so far, and is way beyond most pre-university level courses. Still, we can say with certainty that the field is simply a constant E times the direction r hat, which is from the positive plate to the negative plate. If you are curious about what E is in this system, it is the charge density of each plate, denoted by sigma, divided by the permittivity of free space epsilon naught times r hat. This expression was found via Gauss's law, which we won't go into in this course. Nonetheless, we can clearly see that the magnitude of E is independent of our position in space, and only depends on the charge density of our plates. Now obviously, in a real capacitor, the plates are not infinitely large, so the field lines change like so. However, you can still see that towards the center of the plates, the field is very close to being uniform, and almost acts in the same way as in our infinite capacitor. Therefore, we often use the infinite plate capacitor as an approximation to the field in a real capacitor like this. One small nuance we should recap is the relative permittivity. If you remember from the last lecture, the Coulomb force decreases when the system is not in a vacuum. This also more generally applies to electric fields. So, if the field within our parallel plate capacitor is E vacuum, and we change the medium between our plates to say iron, the field within iron is simply 1 divided by the relative permittivity of iron times the field in a vacuum. Let's now summarize the contents of this lecture. The electric field due to a charged system at any point in space is the force experienced by a test charge at that point in space divided by the test charge. In other words, E equals F over Q. The electric field due to a point charge Q1 is simply E equals Q1 over 4 pi epsilon naught R squared times R hat. Electric fields from multiple point charges add vectorially to get the net field. Field lines follow the electric field vectors and indicate the path a positive point charge would follow if placed in the field. A negative point charge would move in the opposite direction of the field. Denser electric field lines indicate a stronger field. We can sketch field lines for both discrete and continuous charged systems. Between two infinitely large oppositely charged plates, also known as a parallel plate capacitor, the electric field is completely uniform. The electric field within a medium other than empty space is the field in empty space times 1 over the relative permittivity of that medium. So overall, the electric field tells us how a charged system influences the space around it. It tells us where a charge will move if placed in this space. However, while we focused on how charges exert forces via electric fields, we haven't yet really explored why we're doing all of this. The key lies in the energy associated with these interactions. Moving charges through a field transfers energy from one place to another. This is key to electricity, where we transfer energy by manipulating the flow of electrons. In the next lecture, we will introduce the electrical potential energy, work done, and electric potential, which are essential for understanding how circuits work.